All right, guys. So there's a bonus question related to 95% of the data. Where was it? So you guys, if you looked at the bonus, you remember that? If you have a normal distribution, you have a little mean in there, is that cool? Where's most of the data? Yeah, and anything that's normally distributed. For example, heights are normally distributed. Who would these people be if this was heights? Tall-ass people, right? I came off a Southwest flight once. Anybody know Manute Bowl?
No way, you're on his flight.
I wasn't on his flight. Came off this flight, and you look down the hallway, it's gathering, and then you see Manute Bowl just kind of like another person's worth of person above everybody else. He was 7'7". So I talked to people on the flight. They said, yeah, when he sat down, his knees were next to his chin. Anyway, so these are people, if you saw them, you do a double take. Same thing down here, right? If you saw somebody that was 4 foot tall, you would do a double take. Why? Because it's not normal to see this. Not that they're not normal, but it's not expected. You with me? Most people should be in here. That's why that's kind of like described by the shape of this. It's got the biggest hump in the middle. That's where everybody sort of should be. And then there's going to be some outliers, right? So you guys decently cool with that? Okay. If I go up and down one standard deviation, one step, that thing I keep making you guys do. So this is mu minus a sigma, mu plus a sigma. And let me call it by its z-scores. What would this be as z-score wise? How many steps did it take? 1. This would be what? -1. This would be 0. I love it. So within one standard deviation, that should sound familiar, there's known to be, for a normal distribution, there's 68% of the data. This is 68%. So for example, if I knew that the average height for an American male was 69 inches with a standard deviation of 2.8, which is what it was the last time I looked at it, which admittedly was a few years ago, but oh well. Between what two data values would you find 68% of the men? Well, you would just go up. Where would you end up if you go up one step? Don't say no 70. How big is each step? 2.8. So where do you end up? 71.8. Go down. 66.2. So you would expect. So if 68% of all American males are between the heights of 66.2 inches and 71.8 inches. Why did they make the door as tall as they did? Because they could figure out. So here's the door height. So they could figure out how many people will have to duck and how many are they comfortable with making do that. It's sort of like a PR thing. Have any of you guys ever flown on a plane? Anybody? Ever? Anybody never been on a plane before at all? And want to admit it? All right. I remember my first time. So you love it or you hate it. I loved it, thank God. So good luck to you if you do get on one. Hopefully you're in that category. Anybody ever been bumped off their flight? Been bumped? Yes? Involuntarily? You voluntarily took, you know how they say, if somebody will come up here, we'll give you $400 and, so this is, please somebody come up here. So why the shit? Why would that happen? What are the airlines doing? Overbooking. Why would they do that shit? Some people don't show up, so they got to hedge their bets. So it's a little bit of a balance between, if we overbook, there's going to be bad PR. If we underbook, we're going to lose money. So they have people that are always analyzing the data and telling them how many tickets they should sell so that they will have a small chance of being overbooked. They want to make this chance small. And they also want to make the chance small that they'll be underbooked, because that's when they lose money. So they probably lean towards overbook more. Does that sort of make sense? Okay, maybe. So you can see the immediate usefulness of these ideas in the real world. Okay. Keep going. If I go one more step up and down, I'm just going to put the z-scores down here. I didn't really do this to scale very well. Within 2 standard deviations, there's 95%. That's how you do the bonus problem. You go for the mean up and down 2 steps, you'll find 95% for a normal distribution. If it's not normal, it could look like any freaking thing. So I got 1 step up and down, I got like barely anything. If it's normal, I know a lot more about it. More of it's got to be in the middle. Yes?
For the 2's on the outside, do you take the 66.2 and minus it by 2 or the 69?
Yeah, you take another step down. Either you take 2 steps down from 69 or 1 more step down from here. It's going to be the same
So
place,
you can
right?
do 69 minus 2, right?
Of course you can. 69 minus 1 is here, 69 minus 2 is there, but this is already subtracted 1, so subtract another 1, it's the same number, right? Right? Is everybody cool with that? Sounded sort of like an Abbott custom, I think. So if you subtract another 2.8, is that 63.4? Add another 2.8. So, but there's 95% within 2 steps. And then within 3 steps, there's 99.7%. So within 1 standard deviation, there's 68%. 2, there's 95%. Within 3 standard deviations, there's 99.7%. This is called the empirical rule. Empirical is a word that relates to science, because empirical is the idea of observations. So by observing normal distributions, we've seen this happen. So therefore, empirical freaking rule, right? Sort of like if you flip a coin 1,000 times, how many heads would you expect to show up around? You toss a coin, flip a coin 1,000 times. Well, first off, your life, something's going to happen. But if you're flipping coins just to pass the time, that's kind of a bad red flag. But if you flip a coin 1,000 times, around how many heads do you expect to show up? 500. So if you get 800 heads, that's evidence of what? Somebody messed with that coin. You guys see that? Let me say this again. If I got 503 heads, is that freaky? No, it's not freaky at all. In fact, it's almost freakier to get exactly 500 heads. Think about it, right? If you toss a coin 20 times and you get exactly 10 heads, that actually is a little freaky. You expect close to 10. You guys semi with me? Yes, yes. So this idea of where does unusual start? Let me say this again. So like, where does an unusual height start? Well, what would be like an unusual chance for something to happen? 5%. If something has a 5% chance of happening, would you say it's unusual when you see it happen? 5% chance you'll see somebody that's 3'8". You see somebody that's 3'8", and you're like, well, that's unusual. I don't see that all the time, right? If you see somebody that's 5'7", you're like, whoop-de-doo, good for you, right? So this whole idea of where does unusual start? So I expect 500 heads. 800 we could all agree, that would be weird. Would 600 be weird? Would 517 be, I don't know. That later we're going to actually know how far do I go from 500 until I can officially call it unusual. It would be evidence that something's happened to this coin. So a big thing about statistics is this enough evidence that something has changed? So it's going to be a huge deal for us later, in a couple weeks. Later this semester, a couple freaking weeks. Okay. Y'all look shell-shocked. Empirical rules in that book. So maybe you could look that up. Let's see, what else I want to say about that? I think that was it. If I have this formula here, this is good for if I want to know the z-score. What if I know the z-score? Like, let me give you an example. You guys are going to do the math automatically without even a formula. Maybe. Let's see if you guys can do this. Let's say the mean for something is 80, and the standard deviation is 10. Right, let's say this is grades on a test. What test grade has a z-score of 1.5? What does that mean to have a z-score of 1.5? What does that mean? Is it a good place to be? Is it a good grade to have? A z-score of 1.5. What's a z-score tell you?
How many standard deviations go our way?
Yeah, exactly. So it's positive, so am I above average or below? So right there is a good place to be. Am I decently far above average? Yeah. Can you guys tell me what the test grade is exactly? How'd you get that? If I go 80, how far away from 80 is this test score? 1.5 of these. So I go 80 plus 1.5 of these. Please tell me that just makes freaking sense. It's 1.5 steps away. Okay, let me start there and go 1.5 steps. So let's look at the algebra to catch up. So you're right, that would be 95. So can somebody, you guys take a minute and show off your beautiful algebra skills, because that's how you got into this class. Solve this for x. Solve this equation for x. You know, like, I thought that was never going to happen to me again. No, it's like the most important thing to do with anything math related. What's the worst part about this equation when you're trying to solve it? The fact that there's no decimals. Well, equal sign makes it an equation, so I can actually do something. So that's a good thing. The fact that there is a bottom, there's a denominator, there's a fraction, yeah. It's an equation, though. I can kill shit. That's the beautiful thing about equation. You don't like the fraction? Kill it, right? When I teach algebra, it's very violent. I always have like Game of Thrones scenes in my head. Battle the bastard. All right. So how do I kill it? Multiply by sigma, right? Dead. So I get z sigma equals x minus the mean, and then how do I get x by itself? Yeah, add the mean. So I get mu plus z sigma equals x. What is this? Mu. What is this? Z. And what is it? So we just naturally did what the algebra eventually told us to do, right? So algebra isn't separate from what makes sense. Algebra is a way to represent what makes freaking sense. Man, so you guys are like, you're not going to convert me that easy. I'm like, I don't care. It's just true. Too bad. You guys feeling all right? You guys all right? No? You guys are okay? I'm worried about you. You all right? All right, so that's a little formula we'll have on a formula sheet for later. Here's something right now. Let me just tell you this. Since we're talking about z-scores, I'm going to ask the same question on the last the two tests and the final. I'm going to ask this question. Students are always like, just tell me what's on the test. Right? Students are always like, just tell me. I'm telling you right now that this is going to be on the test. I always get over half of the people get this wrong still, even though I'm telling you it's going to be on every test. So please change that for me. I'm going to ask you a question like, what does a z-score tell you? That's it. What does a z-score tell you?
How many standard deviations?
Yeah. How many standard deviations from the mean to the data point? That's it, right? So my God, there. Should be a gimme. Should be, right? Okay. We'll see. I love you guys. At least you're all writing that down. That's good. What if I said, what would a z-score of 2.78 tell you about a data point?
So you're 2.7 deviations away from the...
Yeah, that data point is 2.78 standard deviations away from the mean. Even better would be above the mean, because it's positive. But I'd take away from it. Should be easy. A gimme. A gimme. We'll see. We'll see. I'm so hopeful that I'll break the 50% barrier. It's kind of disheartening. Okay. So let's transition away from this. We're about to get into chapter 3, which is all probability. So you guys, I want to do two things with you. I will do this first thing with you. I'm going to participate myself. Yay, Jeff. And it just involves writing down a number. Not any number. I was born September 21st. Anybody else born September 21st? All right. That would have been a quick end to this. What do you think are the chances that somebody else in this room has the same birthday as you? Not the year, but the date, month and day. Somebody has the same birthday. Not as you, but just two people in here have the same birthday. Think there's a decent chance?
4%.
Better than that. It's over 50%. With a number of people in this room, a teacher, would put money on somebody having the same birthday as somebody else. The reason that our brains aren't quite capable, we think about ourselves. Nobody's got my birthday. The shit. And we're not aware. How many chances are there for two people? Well, how many pairs of people are in here? An insane number of pairs. I can pair you up with everybody. And then I pair you up with everybody. And then I pair you up. Holy shit, this is the first 3 people. Do you see how many pairs of people are in here? A lot of chances for that to happen. So, do this for me. I was born September 21st. So I'm going to put down the number 21. Write it nice and strong and big. I'm going to ask you to raise it. I have to be able to read it. Just the number. So if you're born March 11th, you put 11. If you're born December 31st, you put 31. You guys understand? Don't lift it up yet. Some guys might realize I'm going to call you by month so I can keep this straight. Is everybody playing along? Just put a number down on a piece of paper. Just do that for me. Maybe make it your birthday. That'd be even better. All right, where are my January babies? Raise it up high. 17, 16. Look at that. That's hilarious. I almost had it right there. That's all the January babies? Where are my February? February. What's it say? First? All right, and 12th and 18th. Okay. January, March. March babies. First. That says something. 6th. 25th? Who else was February? What am I? March. All right. April. I haven't got it yet. Shit. I could be losing money. 5th, 22nd, 11th. I appreciate that. 22nd. Wait. 22nd. There it is. Look at that. Oh, birthday twins. Where am I at? March, April. That was April, right?
Yeah.
May. Let's see how many we get. I got one pair, right? 31st. All right. This is freaky man.
57.
Yeah, help me out here, buddy. May. You're born in May? May 7th. Is that what that means? Okay. I was like, I didn't know how long that month was for you. Maybe your mom was like, that was a long ass month. 28, 13. I'm not joking at you. I'm sorry. I don't think we had one. 4th, 13th, 28th. Okay. April, May, June. 12th, 24th, 24th. Look at that. Holy shit. Another couple of... So now I've got 2 pairs, right? And some of you guys probably really thought to yourself, there's no way. July. No Julys. 28th. I was thinking, what's 9 months before July? It's a low season. August. There we go. Somebody's alive. 13th, 31st, 10th. Look at this. It's 3 pairs. Who's back there? What do you got? 29. Okay. That's my little brother's birthday. It's crazy. August, September. 8th, 5th, 28th, 21st, 11th, 19th, 9th? Okay. All over the place. September. Of course, 9 months before that, it's cold. September, October. I love you guys. Okay, here we go. 1st, 15th, 8th. 15th. Is that 15th right there? What is that? That 4 so far? 26, 11. Was there another 11? Right there is 11. What is that? 17. Oh, you got me excited. 29th. Okay. Crazy. Where am I at? November. Was that November? No, this is November. 30th, 2nd, December, babies. You're proud about it. What is it? 18th, 24th, dude. Christmas Eve, baby. 15th. There's all 4 pairs. That's good. Holy shit. Anybody surprised by that? I'm a little surprised I got 4 of them, but I knew they were going to be I expected a couple, to be honest, with this size group. All right, here's the second thing about now, that's an example of how our brains can't really, we're not hardwired to understand probability beyond a certain point. Living in San Diego, if you are at a certain place at a certain time, you might just stay there for a while, if you're like me, because of traffic. I'm like, I missed my window of opportunity. There's a high chance I'll hit traffic. I think I'll just stay here for a while. Anybody else like that at all? There's certain times of day it's just blood red when you look at Google Maps. You're like, I don't want to get in that flow or non-flow. Any guys ever heard of the Let's Make a Deal show? All right, so it used to be at the end of the show, a contestant could give up their prize and get a chance to pick one of 3 doors. Okay? You guys ever heard of this one? It's not a joke. But one of the doors has like $25,000 or a car, and the other 2 doors have goats or something. Now, of course, if a contestant is wanting a goat, that would be great, but it's just something bad, right? And it used to actually be goats. What's the probability then that you pick the door with the prize?
1/3.
Yeah, there's 1 door that has a prize out of 3. So probability is always the number that match what you're looking for divided by the total number of things that could happen. 1 thing matches the prize divided by 3 total things. Somebody pick a door. I heard 2. All right. So in my head, I have a prize, and then the other 2 are goats, right? Now, here's the trick. So there's a 1/3 chance that whoever said 2 has won the prize. You with me? So what's the probability you didn't win? 2/3 chance you didn't win. So probably didn't win. You could have just put lost, Jeff, but too bad. 2/3. Okay. Now, here's the trick. I open a door and show you a goat, and then I ask you, do you want to switch? So I open up door number 1 and I show you a goat. Little mutant spider goat. Right? And you're like, I don't want a mutant spider goat, so I'm glad I didn't pick that door. Should you switch, or does it make a difference? Say again? These did not change.
Yeah, that was both possible.
So the probability this door has a prize is still only 1/3. The probability this door has a prize is now 2/3. And the reason we don't realize that is, why did I open that door?
Make you second.
What's the most likely thing you did when you picked that? Did you pick a prize or no? If you pick a door, it's more likely that you didn't get the prize, right? So if that's a goat, and I'm going to open a door, I'm not going to open the door with the prize, just so you know the prize was here. Right? That's where the prize was. There's a goat back there. So when you pick a door and I say, let me open a door, let me open one for you to show you and then see if you want to switch, I'm not going to pick the one with the prize or else the show is over. So more often I'm going to pick a door because it's the only door that I can pick. So this is still a 1/3 chance that this was the door with it. So when I open that door, this door now twice as often will have the prize. Now I'm not saying you'll switch and you'll win, but if you switch, you'll have double the chances. They actually did this on Mythbusters. They set up the whole show. They had all these people come in, volunteer to come in, and they actually empirically observed, not just theoretically, that there were twice as many wins if you switched. You guys follow? Now watch, if I did 100 doors, this would make a little more sense. Here's 100 doors. Oh my God, Jeff, okay. Pick one. Okay, I picked that one. I'm going to open up 98 other doors. I'm going to leave one door closed. So what the hell is probably true about that one door? Freaking has the prize. So that's just this problem taken to an extreme. But this is so misunderstood by people because we don't understand probability. Why isn't it just 50% because there's 2 doors? Because me opening this was new information. It was, do you understand? It didn't just become, that door's gone now. I chose that door for a reason. I'm sorry, I was talking over something.
So like that show Deal or No Deal? Where you
Oh my God.
You pick one case and then you have 100 cases?
Yes.
Does that even like further confuse things?
show's got so many things to it. I haven't watched it since Howie Mandel was on there. I don't know, is he still on there? Is it even still happening? Ooh, okay.
Let's open that case.
The whole thing is about, it's interesting because if you ever play poker, you know what pot odds or expected values, that's how they calculate what to offer you, is based off of the probability that you got it or didn't, right? When they offer to buy the case or whatever. Anyway, I don't want to talk too much about that shit. Because, I mean, 1 out of 100, you almost definitely got something not that great, right? Okay, how are we doing? Everybody okay? Everybody okay? Which part? So the door thing.
All of it, like, I still don't understand how it would be a 50% chance.
Now stay with me here. This is basically the same thing here with 100 doors, right? So you pick this one. And then I open up every other door and show a goat. There's a goat behind every other door, and I leave this one closed. So what did you pick? You almost definitely picked a goat. Because there's 100 doors. You've got a 1 out of 100 chance you pick the prize. You with me?
Mm-hmm.
So why did I not open this door? More than likely it's because that door has the prize. I just showed you goats behind every other freaking door. So what's more likely? You pick the prize, or the prize is behind the door? Well, that's more likely. That's 99 times more likely. Right? Or 98 times likely. So would you want to switch here? Oh, hell yes. Here you'd almost be guaranteed to win. With 3 doors, it's 1/3 versus 2/3, so 2 out of 3 times you'd win if you switched. I like it. All right, I got one. And the rest of you guys are like, I'm just going to shut up till we move to something that makes sense. All right, now I'm not saying this is an easy problem. I'm saying actually that most humans don't understand this. I'm hoping that maybe, if you think about it with 100 doors, it makes a little more sense. There's a door I didn't open. Why? Because that's probably where the freaking prize is. Now, if you happen to pick the prize, I can just pick any door to not open. But how often will that happen? 1 out of 100 times. So 99 out of 100 times, that other door I didn't open has the freaking prize. So shit, yes, I'm going to switch. It's like, thanks for pointing that out to me. Right? Now, if you switch and it was here, then you really feel bad. But it's a really small probability. Okay, maybe. Maybe. Yes. Maybe. This is one thing I love statistics about, is it's the most honest math. We get an answer, but then there's a chance that it's off by a little bit. Why? Because what do we normally deal with in statistics? We deal with samples. And do samples always have the real information, like the population information? So if I took this row and got an average age, is it going to be the same as the average age for everybody? Let me say this again. If I took this row, got an average age, is that the same as the average age for everybody? I put money on it not being the same. So sample's always going to be a little off. So statistics is always going to be, there's a chance I'm wrong. Right? But that's life. That's why I love it. That's why a lot of people hate statistics, because they expect it just to tell them what to do. And all statistics can say is, oh yeah, if you do this, you have a higher chance. Doesn't mean you're going to win. It just means you have a better chance of winning. Right? Okay, enough of that vague, weird shit. Let's get down to some brass tacks here. So the basics of probability. I think you guys, let's see what we know. Let's do the really boring but very classic problem of
There's 4 red poker chips and 5 blue poker chips and 11 green poker chips.
So if I pick 1 poker chip, what's the probability I get a green poker chip?
1/4.
Who to what?
1 over 20.
Nope. So remember the basic idea. Why should green be the highest probability chip? Because there's 11 freaking green poker chips. So what's the basic idea of probability? The number that match what you're looking for divided by the total things that could happen. Let me write that down. Number of things matching what looking for. Let me just talk like a caveman for a minute.
Things match what looking for other.
Divided by the total number of possibilities. So in this case, what will the bottom be for any question I ask you? 20. It's 20 chips, right? So there's 20 things that could happen. Out of those 20 things, how many match what I'm looking for? 11. So you got a better than 50% chance of getting a green poker chip, right? So if this was a game where I was like putting money on which chip you think I'm going to pick out, then the best bet would be green. Now, of course, that would also give you the least return, but I'm not going to get into casino bullshit right now. If you came to this course expecting me to teach you how to win at craps, forget that shit. I'm not really interested enough to figure out the math behind that. What is that as a decimal? Yeah, how do you make it out of 100? You multiply by 5, so 0.55. So 55% chance. Everybody with me so far? So that's the basics of probability. And if I ask you, what percentage of the chips are green? 55%. So see how probability and percentage are related. They're very often the same thing. If 11% of you are left-handed, what's probably pick a left-handed person? 11% chance I pick a left-handed person. How many of you guys are left-handed? Just out of curiosity. 1, 2. Okay, 2 out of roughly 50. So it's a little bit lower than average, but you never know, right? Small sample. Okay. That's all I want to say about that. The other shit would be boring. So let's make something a little more interesting. Let me just write this down and see what you guys think about how to interpret this. Maybe a little more explained. Oh, sorry. Say yes, no. It doesn't really matter where I put them. Man, I like how I did 3. Yeah, sure. Man, woman, other. So then I could ask people a question. So if I put this down here, for example, okay. So we're in a gender fluid society, so I want to have that other option. So what's 52 mean? 52 women said no, I like it. Right? You guys see that? What does 3 mean? 3 others said yes, I like it. Okay, good. Right? So that's the first step. Sometimes people don't read this correctly. Now, why am I going to do this? Why am I doing this? Yeah, because what's probability is based off of? Out of the total. So I want to get all the totals, and then the total. Please, dear God, don't add these people to these people, because they're the same people, right? So you can kind of check yourself. So you get 108 plus 5 is 113, and 51 and 62 is 113. Yay! But don't put 226. Where'd you get those other people's freaking? All right, please. Is everybody with me? And again, just to remind you guys, if you're not, there's at least 10 other people that also aren't. Speak up. Trust me. Let me ask you a very basic question. If I pick somebody from this list, what's the probability I pick somebody who's a man? Yes, 49 men out of 113. Now help me out. What is that? It's a decimal. Look at that. Kick ass. 4 places. Hopefully it's rounded correctly. Double check. Not that I don't trust you, but I don't trust you. It's like a friend of mine said, I trust you, just be careful. I'm like, that doesn't really jive, but oh. All right, that's groundbreaking. All right. So let's have something more interesting. Let's see what you guys think about this. What's the probability that I pick somebody and they are a woman or they said no? So if you do this, if you do 59 plus 62, what's wrong with that? Well, that's number one, is you get more than 113. If you ever get a probability that's above 1, that's an issue. Right? You can't have a bigger than 100% chance. There's a 120% chance of rain tomorrow. It's going to be super rain. The drops are going to hit you twice. So what is really just more physically wrong with adding 59 to 62? 59 is these people, and 62 is these people.
It's all the women that said no, you missed it.
I've counted these people twice. That's not fair. What the shit? So how do I do this then? I can be smart about it. If I did all the no's plus... Is that still going? All right. Plus 7, right? Why just plus 7? Because who's the only women that I haven't counted yet? Those 7. Now, to be honest, you could do 62 plus 59, but then you have to subtract these guys because you counted them twice. And that's still 7, isn't it? 59 minus 52 is? 59 minus 52 is? 7, which only makes sense. Yes?
Isn't it just as easy to add 59, so that's all the women, plus 8 for no on men, and then 2 for
Yeah,
no
so you
men?
could do it this way or you could do it that way. Yeah, either way. As long as you don't double count these guys. Totally. Kick ass. Okay, so then you get divided by 113. So what do you get? You get 69 out of 113. Whatever the hell that is.
Are you dividing by 113?
Say again? Sorry?
113 because that's in total.
Yeah, that many people out of 113 total people. Say again? Women or no? Okay. So, all right, you ready? Or, so you got or and you got and. Okay? Or is the one we just happened to do first. Or is the nice bouncer at a club. Or is the bouncer that says, all right, to get in here you got to dress nice. Shit. Or you got to have a lot of money. Shit. Or you got to drive a nice car. Shit. Or you got to know Joe the I know Joe the bartender, so I get in, don't I? So the or bartender is going to let more people in because you don't have to follow everything. You just have to follow at least one thing. This or this or this or this. So notice how the or is going to be bigger number than either of these alone because you can be a woman or you could say no when you come in. Right? So all these people come in and all these people come in. These aren't different people. So that's why if you add this to this, you better subtract this off because you've already let them in. Right? On the first, does that make sense? Now, like was mentioned earlier, and like I showed earlier, you could be a lot smarter about it. Just if you do 62, just add frickin' 7 because you already added this. So don't add it twice in the first place. That's great. The reason I'm writing this down is it's related to the formula that we're going to use. Here's the thing about probability formulas. Okay? They often get in the way. If I have a situation where I can count everything, don't use a formula. You'll see why. It gets in the way. Have I even written the formula down for what OR is? No. Did we figure it out? Yeah, okay. In fact, we have multiple ways to do it because we kick ass. All right. A couple more things, and I think we'll take a break. What time is it? Yeah, sure. So it's probably that I picked somebody who's other or said yes. So they could say yes, and they'll get in. Or they could be other, but how many others have I not counted yet? 2. So how many total do I have coming in? No. I didn't count these yet. Okay, and all these people plus these 2 I haven't counted yet. Or you could do 51 plus 5 minus 3 because you counted the 3 already. Right? So you could do 51 plus 5, but then how many did I double count? 3. And isn't 5 minus 3 the 2 that you haven't counted yet? That's why mathematically you can look at it either way you want to. You could also do 5 plus 7 plus 41. Just make sure you count everybody that this statement wants to get. Out of what? Yeah, 113. So this will be 53 out of 113, and whatever the hell that is. Who is it? 469. 4690? I like it. Sweet.
So the 5 minus 3 you got because you did 3 and 2, right? For the yes and no forever.
So if I add 51 to 5, if I add these people to these people, which people did I add twice?
All the people that said yes and then
I added these people twice. Right, so I could do 51 plus 5 minus 3. Or I could just do 51 plus the 2 I haven't counted yet. Doesn't that come out to be the same number? Of course it does. Math's got to work whichever way you look at it. Okay. I love you guys. Let's write down the formula for OR right now. You ready? What's this 51 out of 113? That's the probability of yes, right? What's the 5 out of 113? That's the probability of other, right? And what is the 3 out of 113? Who are those people?
both.
They're the ones that said yes and other. So in general, that would be subtract off anything that's A and B. So OR is basically add. Because OR says you could do this, or this, and that's more people, or this, and that's more people. So it adds more and more and more and more. So let's talk about and. How do I calculate and? And then we'll take a break. And is the mean bouncer. And is the bouncer that says, all right, you get in the club, you got to know Joe. I know Joe. And you got to dress nice. I'm out already. And you got to have a lot of money. I'm walking away, dude. Stop it. Has anybody ever applied for a scholarship? Anywhere? If you haven't, you're crazy. That's all right. Back in the day, Jeff's old. He remembers the days of pre-internet. Yes, there was a time. It wasn't a dark time either. We were fine. There's this big-ass book in the financial aid office of scholarships. So you come in, set up the time to come in, you crank that thing open, and it'd say, okay, must be a math major. Check. And must have a GPA greater than this. Check. And must run blah, 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 blah. And the very last one, and must be a woman. Put that first. What the shit. So, and is the mean bouncer. He's the one that makes the number smaller because you have to meet all the requirements. Or is, just got to be one of them. Come in. So this is always going to be a bigger number. And if I said what's the probability that it's a man and they said no. So they have to be a man and they said no. How many of those? We can do this.
7.
No. They have to be a man and said no. 8. And do you see why and is very often called the intersection? Man and said no, 8 out of 113 chance. There's 8 that match what I'm looking for out of 113 total. You see how I made the number much smaller than either one of these? Because it's got to match both. So and is called intersection. And on a chart, that makes so much freaking sense. Look, it's where they intersect. Right? And that's going to make the number smaller. Okay, let's. I think we can take a break. What do you guys? I don't even care what you say. We're going to take a break. So, come back 5, 10, 15, 20. Come back 15 till. Come back at 10:45. By that clock there. So you might want to synchronize your watches.